titles of exercise doesn't tell you it's assignment 1 or 2.
No, I posted them at the bottom. I posted the actual pages with the questions at the bottom. On e-class, just look in e-class.
Under exercise or under assignment?
Under exercises for those who are using the old book. That's what I said. Exactly. Yeah, under
I checked yesterday and those one under exercise.
Let's see.
Let's tell what assignment number is.
Maybe I'm not sure. Has anybody seen it? Exercises from new book.
Right. Yeah, so let's check this.
So, depending on which chapter. So for the linear algebra chapter, there it is.
So this
There's
is for
6.
assignment?
I don't remember exactly because some assignments are from different pages.
Oh, okay. So match that.
These are all the exercises at the end of each chapter. So you just go through it and try to find it. So, in the next short while, the one thing that we're going to cover, just an introduction to what you guys do in CivE 660. In CivE 660, you take everything that we talked about today and you apply it with some restrictive assumptions to make your beams. So in general, in general, what finite element analysis is able to do, based on everything that we study in solid mechanics and in continuum mechanics, what finite element analysis is able to do is to take an object like this, and given some boundary conditions of forces and of displacements, it's able to give you an object that deforms with very large deformations. And as long as you have adequate measure of stresses or adequate measures of strain, you're able to deform things with very large deformations. However, for us to be able to do things by hand, we had to develop the beam approximation, in which we have put very restrictive assumptions on the possible deformation shapes of beams. And the restrictive assumption that we put is that plane sections has to remain plane. So the restrictive assumption for beams perpendicular to the neutral axis. If you have a beam before, deformation, and this is the neutral axis, if you draw any plane here, after deformation, you enforce this plane to stay plane, and and perpendicular. So you tie all those points together into one plane, and you enforce that this plane stays perpendicular to the neutral axis. Now, this is a very restrictive assumption, but allows us to solve things by hand, and this is an objective of the first assignment is to just find closed form solutions. Are you able to find a closed form solution to the equilibrium equation based on whatever assumptions we put? And so this is what we call, when you're using finite element analysis, when you use beam elements, you have the option of using something called the Euler-Bernoulli beam. For this Euler, or the finite element analysis calls it the Abacus calls it the cubic permutation. And we will understand why it's called the cubic permutation. Or there's a less restrictive assumption, but still very restrictive, which is the Timoshenko beam. Where plane sections remain plane, but not necessarily perpendicular. So you allow that plane sections to form in shear, but still very restrictive in saying that this has to stay plane. You cannot allow a deformation like this. So whenever you're using beam, you need to realize that you're assuming this plane sections remain plane, and hence you're able to remove this whole plane, this whole beam, and just replace it with the neutral axis of the beam. Because knowing the location of the neutral axis of the beam, because of that perpendicular plane, you know the location of everything else. So I don't need to know anything except the location of this point. Because if I know where this point is, I know where this whole plane is. Here, if I know the location of this point and the shear angle, I know everything else. So here, I need y and the shear angle. Here, all I need is y. And so to be able to do the beam, the first thing you do is, instead of looking at stresses at a point, you look at a stress on cross sections. So you integrate the stresses on your whole cross section, and you get a normal force, which is the integral of sigma on 1. You get a shear force, which is the integral of negative sigma on 2 over the whole cross-sectional area. And the reason why we're saying negative here is just because of the sign conventions. In beams, V12 positive, this is the positive V12. In stresses, this is the positive sigma 1. And similarly, V13. And the moment, because now we're not calculating the stress at a point, we're integrating the stress along the whole cross section. Now we have what we call a moment, which is the integral. This is the cross section. This is the. So this is the cross section of the beam. The moment, assuming that this is the positive moment, and this is the distance x2, and this is the positive sigma 1, 1, then the moment, this is the positive, is equal to a negative value because of the sign convention. This is the positive m3, this is the positive sigma 1. M3 is equal to negative this value. The integral of x2 sigma 1 d. And you have also m2, and you have the torsional moment as well. But because we're just going to look at beams in plane, I'm going to look at n shear and And the equilibrium equations, similar to everything that we did before. I'm going to extract the sliver of the material. I'm going to assume that the shear, so I'm going to extract the sliver of the beam with a Q acting upwards on it. I'm going to put a shear here, V. I'm going to put a shear here, V, plus a little bit more. I'm going to put a moment here, again with the positive directions, a moment here, plus a little bit more. I'm going to take the sum of forces in the vertical direction is 0. I get a differential equation that tells me dV by dx1 is equal to Q. And I'm going to take the moment around here, say equal to 0, then I get a relationship between this moment and the shear. So this equation of equilibrium is equivalent to the equation of equilibrium that we introduced before, but after integration. This was just at one point. This is after integration over the whole cross section. So I don't see stress, I see shear instead. I see a shear force because I integrated this equation on the whole cross section. So after this, I'm going to use the deformation assumption. So my deformation assumption states that plane sections remain plane. Because plane sections remain plane, I'm going to see the following. This is the beam before deformation, point, and I'm looking at a point. At a distance x2 and a vertical distance x1. After deformation, this point, this is point A, so I'm looking at a point underneath point A. I assume that the beam has moved vertically with a function. The neutral axis has moved vertically a distance y, which is a function of x1. Y changed according to x1. And because plane sections remain plane, this angle stays 90. And because I'm using small deformations, theta is equal to tan minus 1 y prime, which is equal to y prime. Small deformations. And so, the new location of the point is equal to the old. This is x1, this is x1. The new location. The new location of the point, small x1, is equal to capital X1 minus x2 sine theta, minus the small distance, and the vertical displacement of the point, the vertical position of the point is equal to y plus x2 cosine theta. And x3 stays the same. So small deformation tells me that sine theta is equal to tan theta is equal to theta is equal to dy by dx1. The new position is equal to those values. The displacement is equal to the old position, to the new position minus the old position, x1 minus x2, so you end up with this vector, u is equal to negative x2, and theta is dy by dx1, y and 0, and so when you calculate half the gradient of u plus the gradient of u transpose, which is the small straight matrix, you'll find everything is 0 except epsilon 1. Epsilon 1 in this case is equal to negative x2 d to y by dx1 squared. So the constitutive law for such problem, you say, you ignore Poisson's ratio, say sigma on 1 is equal to E x multiplied by epsilon on 1, and you get a relationship between sigma on 1 and this, negative ex2 d2y by dx1 squared, and a relationship between sigma on 1 and sigma on 2, which you are familiar with from beam analysis. Because I'm able to replace sigma on 1 with this, and I have a relationship between the shear and sigma on 1, I end up with a differential equation. The differential equation of equilibrium is an ordinary differential equation. Which is d, I'll just write it again, d4y by dx1 power 4 ei, which you're all familiar with from any beam analysis course that you took before. So this is a differential equation of equilibrium after replacing the stresses with a function of the deformation. So now the one unknown that I'm looking for is that deformation, which is the displacement of the beam, rather than the stresses which appear in the differential equation. So instead of using the stresses in the differential equation, now the differential equation is in terms of the unknown displacement and its function of the loading on the beam. This is an ordinary differential equation of the fourth order, so I need four boundary conditions. Four boundary conditions to solve it, and the four boundary conditions are usually given in terms of moments, shear, rotation or displacement itself, where the moment is actually related to the second derivative of y, because the m is equal to ei d2y by dx1 squared, or the shear, which is basically nothing but the third derivative of the displacement. And so by solving this differential equation, by finding y, you can find, after you apply your boundary conditions, you find y, and after you find y, you find the moments everywhere, you find the shear everywhere, and don't forget that the objective of this is to find the stress, because everything that we're doing is we're designing based on the stress. Sigma on 1 is equal to negative the moment multiplied by x2 over I, and sigma on 2 is equal to negative the shear multiplied by what we call here x2 divided by IB. Now you've done a lot of statics from 270 and all these courses, so you know these equations, you've seen these equations before. But what I want you to get used to in this example, or in the example which is in your assignment, is to get used to drawing, to find stresses and drawing contour plots of stresses on plane objects. Because in finite element analysis, that's what you're going to do, but the software will produce it for you. So let's discuss the first problem in your assignment first. Which you have to solve by or using method. So you're given this problem with a concentrated load here, whatever the value is, and I'm telling you, show that the displacement is equal to a function, a certain function, when x1 is between 0 and 8, and and another function when x1 is between 0 and b. The reason why I want you to solve this by hand is because you'll find that just because there's a discontinuity in shear, now you know the shear force diagram looks like this. And this is d3y by dx1 cubed. Because of that the shear force is not continuous, the solution for the shear force is not continuous, that's why you have two different equations for the displacement. You have a certain displacement function for this half, and another displacement function for this half. And so, for this particular problem, you have to, because we're doing it by hand and we're looking for the exact solution, you have to divide this into two problems, solve the first problem and solve the second problem to find the displacement along this whole beam. In finite element analysis, or in any numerical method, which will be the subject of the next lecture, we don't have to, since we're doing an approximation anyway, I don't have to stick to this very restrictive or very, or I don't need to restrict myself to discontinuous solutions, and I can assume that the approximation actually looks like this. So, in next lecture, we shall find approximate solutions that overcome or that approximate this continuity. Now, for you to solve this problem, what you have to do is you have to do what you know, break it like this. I'm going to put this as positive shear, positive shear. This is the given shear, positive shear. I would like to find y here. I would like to find y here. The boundary conditions are as follows. This is EI. Let's call this y1. EI d4 y1 by dx1 power 4 equal to 0 because I have no distributed load. And here EI d4y 2 by dx1 power 4 equals 0 because I don't have any distributed load. The difference between y1 and y2 is the boundary conditions. The boundary conditions are as follows. Right here, so I need 4 boundary conditions for each. Y is equal to 0. And theta is equal to 0. Y is equal to 0 and theta is equal to 0. So I need 4 more boundary conditions because if you count, I need 4 on the left and 4 on the right. So in total, I need 8 boundary conditions. So this is the first 2, second 2. So I need 4 boundary conditions in the middle. The 4 boundary conditions are as follows. The displacement on the left is equal to the displacement on the right. The beam is continuous. The rotation on the left is equal to the rotation on the right. The moment on the left is equal to the moment on the right. And the shear plus, which is given, plus V2 minus V1 equals 0. So in solving those two differential equations of equilibrium with 4 boundary conditions, and you get your differential equation really quick. Now, you should right away retrieve the numbers that you have in the example. So you get y1 and y2. And you should use, if we have time, I'm going to show you, differential equation solve in Mathematica. Then you write it like this. EI multiplied by y1, 1, 2, 3, 4 equal 0. Comma. EI. So I'm writing both differential equations. Y2, 1, 2, 3, 4 equal 0. Comma. Y1 of 0 equal 0. Y1 or y1 prime of 0 equal 0. Y1 of A equal Y2 of A. And so on. Put all the boundary conditions. EI multiplied by Y. 1, 2, 3, 4. Sorry, 1, 2, which is the second, which is the moment. The moment on the left is equal to the moment on the right. And so on, and then goes your curly brackets, comma, solve for y1 and y2, through curly brackets, comma, in terms of x. If you just write this, you're going to get the solution right away. Or you can do it by hand, which is just a lot of equations and a lot of unknowns to do it by hand. Because you have 8 unknowns, basically. The 4 constants in each. So this is your first assignment, the first problem in your assignment. And the whole purpose of this problem is just to understand that for something like this, you really have to divide your domain. In a finite element analysis, I don't have to divide my domain. I just live with it and assume that my solution has this kind of discontinuity, or that my solution approximates this discontinuity with a function like this. And the second problem in your assignment is similar to this problem that I will show you how to solve now. So, you have a cantilever for this. In your assignment, instead of cantilever beam, you have a simple beam. In Mathematica tutorials, in your Mathematica tutorials, there are examples. There are examples that you can look at to follow this. So I have a cantilever beam with Young's model as 20 gigapascal. The beam is 5 meters long and has a rectangular cross section. The height of the beam is 0.5 meters and the width is 0.25 meters, and a load of 125 kilonewtons is applied at the free end. We need to draw the contour plots of sigma 1, sigma 2, and the von Mises stress along the beam. Also, we need to sketch the principal stress directions at the top fibers and the bottom fibers and the neutral axis and at quarter of the height of the beam at the support. So I want to know the direction of the principal stresses at this point. And I would like to draw the vector plot of the displacement of it. So, the first equation, the equation of equilibrium that I need to solve is this. And the boundary conditions are at x equals 0, y is 0. So this differential equation looks like this. The solution looks like this. So I have 4 constants, 1, 2, 3, 4. And to order to find those 4 constants, I have to use boundary conditions. The first boundary condition is that at x equals 0, at x equals 0, I have the displacement is 0, which will tell me that C4 equals 0. Because when I put 0 for x1, I get C4 is 0. This is y is 0. The rotation here is also 0 because it's a cantilever beam. At x1 equals 0, the rotation is equal to 0. You'll get that C3 is equal to 0. Right here, the moment, I have no applied moment. So the moment is equal to 0, and the shear is equal to positive 125. Remember, this is your positive shear and moment, and positive Q and positive Y. At x1 equal L, theta, the moment equal to 0, which will give you, this is the moment, which will give you even C2 is 0. So at x1, equal L, the shear is 0, the shear is 125, which will give you that C1 is equal to 125. And so when you put 125, you've got your shear. Oh, I'm sorry. C1 multiplied by L plus C2 equals 0. Here, thank you. C2 is equal to negative C1 L. So C2 is equal to negative 125. So now I have my displacement, rotation, moment, and shear. From this, I'm able to say what the sigma 1 is. Sigma 1 is equal to negative m, which is a function of x1. So I'm going to put here function of x1 multiplied by the height away from the neutral axis, which is x2, divided by I, which is a constant. And sigma 2, which is given as negative the shear, which is a function of x1, divided by IB, which are constant, multiplied by another function of x2, which is your Q, which is the moment of area. And if you don't remember what this is, I will cover it in a moment. So basically now I have a beam where this is the origin. Any point, I'm just going to pick a random point here. The stress at this random point is given by a value for sigma on 1, a value for sigma on 2, a value for sigma on 2, and everything else is 0. These are our restrictive assumptions for the beam. I have the stress, I've got everything. I've got the 1 meter stress, that's what I'm designing for. I've got the hydrostatic stress, I can find the strain, I can find anything I want. I can find the principal stresses at this location. The principal stresses will be aligned somewhere because this is, in this coordinate system I have shear, so I need a coordinate, there's another coordinate system at which the stresses are, the stress matrix is there. And so when you look at the solution, right here, sigma on 2 is 0 at the top. And so your stress matrix has only sigma on 1. And so your principal stresses are in this direction. Tension and 0 in the other direction. At the bottom, we've got compression and 0 in the other direction. So this is the direction of your principal stresses. In the neutral axis, you have sigma on 1 is 0. But you have the maximum shear stress. And so right in the neutral axis, you'll find that there is another point system, perhaps this, yes. This will be tension, and this will be compression. So in this coordinate system, the stress is diagonal, and so you've got tension in this direction and compression in the other direction. And that's why in concrete beams, for those who are civil engineers, know that closer to the support, because I'm worried for a cantilever beam, because I'm worried about what we call shear stress. In fact, what I'm worried about is not the shear stress. What I'm worried about is that tensile stress, tensile principal stress. Because the concrete is not good under tension. So for a cantilever beam, you know that you put tension at the top, you put your steel bars, and tension in this direction. In the past, they used to put steel bars like this to take that diagonal tension. But now, instead of using this, they use the shear studs, vertical, which basically does the same thing. And so the one thing, if you're not familiar with this equation, what is Q? I would like to calculate sigma on 2 at this point, or at this point, we assume that sigma on 2 is equal to all these points. Sigma on 2 is equal to minus the shear on this section, multiplied by the moment of area, which is Q, divided by I divided by B, where this is B. Q is equal to the moment of area. This is the neutral axis. If this is T, and this from the neutral axis. This is x2. This is the location of the point where I'm calculating q. And this is t over 2 minus x2. Q is equal to area multiplied by y bar, where y bar is this distance. Area is equal to b multiplied by this height, which we said is equal to t over 2 minus x2, and y bar is equal to x2 plus half the height of that section, which is half t over 2 minus x2. So you can see that q is basically a function of x2.
It's only a function of x2. The rest is just constants.
Okay, so I have a few minutes now. I would like to show you how to solve this beam and how to draw the contour plots and the vector plots. So for me to solve a differential equation of equilibrium, so for example, let's solve these solve. I would like to find y as a function of x, or y1. Let's see if what I wrote to you is correct or not, or 1 and y2. That's the EI multiplied by y1, 1, 2, 3, 4 of x equals 0. The second equation is y2 of x equals 0. You'll get that y1 is a function of x, where y1 is equal to c1 plus x c2 plus x squared c3 plus x3 multiplied by constant 4. Now, because it's a constant, that's why they don't have c4 over 12. It's just a constant anyway. The constant takes that. And so I can simply, if I want to retrieve y1, I can say y1 is equal to y1 of x after you utilize this solution. This is y1. If you want to include the boundary conditions, you include them in the equation itself. So let's say y1 of 0 equals 0. You will see that one of the equations, one of the constants in the first equation will be gone. Okay, I have to clear because I can't use u. I just assigned something to y1. I can't do that here, so I have to clear. So y1 is equal, so I got rid of the one constant because I said y1 of 0 equals 0. Now, be careful how I use the brackets. Y is a function of x. I'm using one set of square brackets. A is a matrix. let's see what A looks like. A in matrix form. A is a matrix that has two values. This is the first value, or it's basically a row that has this value and this value. This value y1 is this function, comma, y2 is this function. So I'm taking the first row in this matrix. That's why I'm using two square brackets. When I retrieve values from matrices or from lists, I use two square brackets. When I'm defining a function, I use one set of square brackets. When I define a list, I'm using a set of curly brackets. So inside the first set of curly brackets, I'm putting all my equations and all my boundary conditions, and then between two commas, I'm putting y1 and y2. Between two sets of curly brackets, this is my two unknown functions, and they're both function of x. So this is how you would solve your first assignment. You don't have to just do it by hand, but you should know how to do it by hand. In the second problem, I want you to draw a contour plot or a vector plot. Let's say my stress S11 ends up being equal to x1 squared, or x1 squared plus x2 squared minus x1 multiplied by x2 multiplied by 1. Let's say this is my S11, it's a function of x1 and x2. I would like to, and let's say S22 is equal to another function. Let's say it's the same for now, S12. And you can form your stress matrix. It's a 3 by 3 matrix. S11, S12, 0, 0, sorry, S12, 0, 0, and then 0, 0. If you want the principal stresses, all you have to do is the eigensystem of S matrix. Now, this will give me an error I would expect, because x11 and x12 do not have any values. Let's see. It didn't give me an error, but it just gave me a huge equation. Function of x1 and x2. So this is the first eigenvalue, and this is the corresponding eigenvector. The second eigenvalue and corresponding eigenvector, third eigenvalue and corresponding eigenvector. You can see how powerful it is because all this depends on x1 and x2. I haven't really given you any values for x1 and x2, yet you can find the principal stresses at any point. So I can plot my S11, contour plot. S11 on the beam, x1 goes from 0 to 1, let's say 5. x2 goes from negative 0.5 or negative 0.25 to 0.25, the length of the beam and the height of the beam. Contour labels true. I want to see the numbers. Plot label S11 in MPA. There's another one, yes. Aspect ratio. Because the beams are usually long and depth is small, you want your contour plot to, you can see it. So let's see 1/3. Shift enter, and here's the contour plot for S11, for example. If you're able, you can put. So this is what I'm expecting you to do for the second problem in your assignment. Alright, and this is it. So assignment 1 is due next week, and what's that? So you have control plot. You also, I wanted the vector plot of the displacement. The displacement is a certain function. Let's say is equal to x1, 0. Let's say this is your displacement vector plot of u, same thing. Instead of control plot, I want vector plots of your displacement on this beam, but this option is no longer here. The plot label is u. Shift enter, and you get a plot showing the displacement of the beam. So you know where every point has gone. And you calculate the displacement because you know the displacement function given as, where is it? I'm just going to go back. Here's your displacement function. It's a vector, so you know the horizontal component and the vertical component. You plot, this is a function of x2 and of x1 because y you already solved for. So you plot the vector plot of your displacement, and you end up with these nice plots. Now these nice plots you're producing by hand. Finite element analysis gives you the same plots, but on a more more geometry that's irregular, and it's just an extension of this to irregular geometries, and with less restrictive assumptions. There's still some restrictive assumptions in the displacements, but less restrictive. Here, there's very restrictive assumptions, plane sections are plane, the stress is sigma on 1. The only non-zero stresses are sigma on 1 and sigma on 2, everything else is 0. But in finite element analysis, we do not have those restrictive assumptions. Alright, do you guys have any questions? Alright, we'll see you next week.